I'm gonna do this last theorem about separability. This is one of, I just really think this is a groovy theorem. And then we're gonna talk about, giving Galois for a while. 8, 4, 6, 3. Okay, so suppose I have a finite extension field, finite dimensional. There's one. If F is separable over K, then F is simple. And being more precise, F is K some. Oh, by the way, I don't think there's a talk today. Actually, it's the math club speaker. I encourage you all to come to the math club too. There might be some repetition there, though. But anyway, she's going to give a talk in. Thank you. By the way, do you have to know off the top of your head what room that's in?
I can look at the email.
Right. So I am going to go to that talk. So I'll be out of my office from like a little after 11 until 12. Talk to me after class if this is a inconvenience. Yeah, let me know when you find it.
Didn't the speaker do the same talk twice?
Yeah, Martin and 103
In the.
103. Okay.
Is it the same?
I thought
at 11:15.
sort of in the following sense. I think she's going to give sort of the talk at your level, you know, kind of the more mathy level here. And I think it's probably going to be more undergraduate, I'm going to say, for the bachelor.
She's doing it back home.
She's doing, what do you call it, integer choice, games. She uses some linear algebra, some combinatorics.
Title for the, I don't know if you can read it from there.
No, I sort of can't.
Now. It sounds like it might be a different talk, I'm sure.
Well, it probably is, but I think that at the core of it, it might be, you know, like I could give 2 talks called norm sets, one for the people that are more mathy, and then one's for, you know, the younger folks. And there'd be different things in it, but there'd be kind of the central thing, right? They'd probably both be worth seeing. So 2, F is a simple extension. If and only if there are only 5 many intermediates. If and only if there are only 5 many. So we pointed out last time that one follows from. So I want to focus on proving number 2. So for number 2, we reduce I'm going to make a reduction as follows. So let F be the normal closure. So in other words, think of it this way. I know that F over K is finite. So just take some element U that's in F but not in K. It's algebraic, so it's got a polynomial. Let's take the splitting field of that polynomial, and that'll be normal. So the normal closure certainly would, well, that would be the normal closure. And the degree of F of K is also. Let's see now. And we discussed this actually in reducing, showing that one follows from two. Now what we have is, in fact, so in particular, it's finite Galois. Extension and so we can concentrate our efforts here. So let's first suppose there are only finitely many intermediate fields. So we're going to assume that we have only finitely many intermediate fields between K and F. Since we find U and F such that right, because run through all the elements of F and look at KU over K. Since F over K is finite, certainly we could find a maximal degree simple extension that lies between F and K. Now, I certainly hope that this is all of K or all of F. If KU is equal to F, then we're done, because now we've got the simple. If not, there is when you remove KU from F, there's at least one V left over. Now I'm going to look at all intermediates extensions of the form. By the way, I think this might be helpful. So this technique. So look at all these extensions of this form. K of U plus AB, where I'll let A be kind of a parameter that ranges through values of K. Now, if K is infinite, well, then certainly this makes an infinite list of possible elements to a joint, right? If K is an infinite field. However, there's only finitely many intermediate extensions, so you've got to double up, right? You've got to pigeonhole some of them. So if K is infinite, then there exists A and B not equal. Because there's infinitely many such things, but only finite many intermediate fields. So you've got to double up somewhere. So if you look at A minus B, This is U plus AB. This is U plus AB minus U plus VB. And notice that this is in this thing must live in K U plus AB. Right, because this is obviously K of U plus, and since these are the same, U plus V, VB must also be as well. Now since this thing is not zero, this implies so what do we get from that? Yeah, B is here. So this implies now I've got both U and V. Notice that um, KU is contained in this, and it's strict because V doesn't live here.
No, the top part. But
Oh, I didn't even see that. You're absolutely right. There we go. See what the problem is here?
Supposed to be maximal.
There you go. This is maximality matrix. Hence, so if we have, there's only finitely many intermediate fields, then we have that F must be simple. That's of course for the case of infinite fields. What if it's finite? The finite case is different but easier. Now, suppose K is finite. Since the 3 F over K is finite, then what can we conclude about F? It must also be finite, correct? Because K is finite and then you have a finite dimensional extension. So again, the module stuff helps. F is a finite dimensional vector space over K. K is a finite field. So basically F as a vector space is isomorphic to n copies of K, which has order of K to the n elements in it, so it's finite. And now, so I'll get it. So now it's clear that F is a simple extension. Anyway, how would you get, just from the fact that F is finite, how would you know it's a simple extension? Okay. So what we have is a finite field, right? What do you know about the multiplicative subgroup finite? Simple. Generated by a single element. Correct. In fact, the only thing we need K for is the zero. Okay. On the other hand, let's suppose that F is a simple extension. I suppose F is KU. Now U is the root of an irreducible monic polynomial. Yeah. Over K. It's finite. Then U is the root of a minimal minimal polynomial. Of course, you're just however you want to think about it. Roots and f of x and k. Right. So what I want to do is I want to count the intermediate extensions, right? So let's let E be an intermediate extension. So we have K is contained in E, which is contained in F, which is K. Well, then U is the root of a monic polynomial over E, right? I mean, after all, U is algebraic over K, so it's roots in polynomial coefficients K. So it's certainly root polynomial coefficients here. E, let me call it something. So U on irreducible polynomial. Coefficients are elements of E. By the way, let me ask you this. What do you know about the relationship between G and F. Yeah, G has to divide F, right? That's gonna come up in a moment, right? But keep that in mind. So certainly, let me point out that U is a root of f of x over e of x, because since f of x is a k of x is an e of x. And that means that if g of x is minimal, it actually must divide f of x, because ex is also a principal ideal domain. Notice that f over this uh, notice that this polynomial here is irreducible over E, but in fact, it's irreducible over this potentially smaller field. Right? Because really, all I need to build this polynomial, perhaps I don't need all of E, I probably just need these things, right? So this extension is a degree M, which is the degree of the irreducible polynomial. And since F over E goes X. Okay? So in other words, E is exactly equal to K adjoined with those coefficients of that polynomial. So E is completely the harmonic divided. So the number of intermediate extensions is bounded by the number of divisors. Uh, but even over splitting here, there are only finite many harmonic divisors. And so in this, I mean, I'm not claiming that F is a splitting field. Even in the splitting field, there's only finitely many monic divisors, right? And those monic divisors are all bounded by the degree of whatever f of x is. That means there's only so many ways that we can put them together. There's only so many divisors of f of x we can get. So there exists only finite extensions. Between. Okay. Okay. Any questions? Questions? Okay, so now we get to kind of embark a little bit on what I think is a lot of fun. So I call this section approaches. Defining the Galois group of polygons. What do I mean by the Galois group of polynomial? What I mean by that is take a polynomial over some field K, and find its Galois closure, right? So for this, I'm going to, I think I'm going to uniformly assume that what I have separable polynomials. So, and in fact, in particular, for this, what I'm going to use most are finite fields, and those extensions are always separable. Finite extension and finite field is always separable, and characteristic zero. And in fact, probably for most of my applications, I'm going to look at the base field being rational numbers. So if I have that situation, I have a separable polynomial. What do I mean by Galois group of that polynomial field? I just mean take a splitting field, which is now normal and separable by assumption, and it's Galois. Find the group of automorphisms, it's splitting field of that polynomial. So let's start with the following proposition. I'm not going to prove much. This is kind of a get your hands dirty section. I'll probably outline proofs for a lot of it, but probably super rigorous with some of the results. Let f of x be a separable irreducible polynomial. Over I'll say and write this way. So f of x and k of x is separable, it's irreducible. We'll say its degree is n. The splitting field of f of x and k which we'll call this f. It's Galois extension of k. Of degree less than or equal to n plus so n. So far into this, there's kind of nothing new here. If you have a separable polynomial, splitting field is normal, so separable in Galois, so it's I'm sorry, separable and normal, so it's Galois. And we also have the result that the splitting field can be obtained for any polynomial considered well, actually any polynomial of degree less than or equal to n factorial. Here's kind of the interesting part. What is more for n divides the order of Galois group. So if you've got a polynomial of degree 6, Galois group has to be divisible by 6. And the Galois group is a transitive subgroup of SN. Um, Let me ask you this, does anybody remember what it would mean for a subgroup to be transitive? Well, let's say a subgroup of SN. Maybe, I don't know, did y'all have a colleague, I can't imagine a colleague, but I didn't mention transitive subgroups, but. Well, it doesn't matter, we'll, so let, H. SN be a subgroup. We say, H is transitive. So let's let SN be, so think of SN as the permutation group of the integers 1 through n, right? H is transitive if for all, I. There exists sigma in H such that sigma I. to J. So what it means to be a transitive subgroup of SN is it's a subgroup of SN, and given any two elements between 1 and n, that is the section unity, any two elements, there has to be something in this subgroup that takes the first element, second, sigma I, sigma j. Why is this true? So how does this compare to this? Well, if, what do I call this? U and V are roots at max. Right, then there exists sigma and Galois group. F of K such that sigma U. Remember that business about the Galois groups, because remember the field extension, the smallest field extension that of K that contains U is K adjoining with U, same K adjoining with V, and they're both isomorphic to KX mod the polynomial, ideal generator of the polynomial, right? So this comes from U, and U is isomorphic to KX modulo. Yeah, here generated by F of X, so your boost, which is isomorphic to KV, because U and V are both roots of this. So there's an isomorphism from KU to KV, and we can lift that to an automorphism of all of the speed. Right. This is why it has to be transitive. How many roots? So it's a separable polynomial, right? That's our assumption here. How many roots of a degree inseparable polynomial do you get? There has to be n of them, right? They're all different. These are your roots, right? These represent your roots. Root 1, root 2, root 3, etc. Right? Any two of these roots, there's an automorphism that takes one of them to the other. Right? And that's exactly what it means to be a transitive subgroup. Right? So you can move roots around in different ways. Okay. This might help too. Let me build you a small table. Thanks. I won't list maybe all the transitive groups, but I'll list you one of every isomer. S2. I can write the entire group down. There's only one transitive subgroup. This group acts on set 1, 2, and there's all, and notice that 1, 2 takes 1 to 2, 1, 2 takes 2 to 1, and you're done. S3. This will be the last one right now. These are all the elements. One of the transitive subgroups of this. Well, one of them is S3, right? Suppose you won't take 1 to 2, there you go. Suppose you want to take 2 to 3, there you go. Suppose you want to take 3 to 1, there you go. All right, and all possibilities are there. There's another one.
Filter generated by 1 through 3.
This is actually A3, but I'm actually gonna write it this way, E, 1, 2, 3, 1, 3, 2. This is A3. If you want 1 to go to 2, use that one. If you want 1 to go to 3, use that one. If you want 2 to go to 3, use that one. That's trans. Transfer subgroups S4. Okay, you guys didn't jump on it, so now I get the easy ones. S4 and A4. All right. Those are actually constant. Three. Cyclic waterfall. Right? Let's think about that. I'll use this. This will be my computation. There's one possibility of cyclic waterfall. One goes to 2, one goes to 3, one goes to 4, 2 goes to 3, 2 goes to 4, 3 goes to 4 somewhere right there. Okay. By the way, there's actually several isomorphic copies of cyclic waterfall, and they're all trans. My number's different. There you go. What's the key here? The dihedral group must contain these, right? So how about that? And I know Matt would be very happy because I wrote 4 instead of 8. Right. So the dihedral group 4, there's not really much you need to check because it has to have a cyclic group 4, right? You might know what the other one is.
Yeah, it's supposed to be support.
No, because I'm only going to look at isomorphism devices, so I consider that covered. Right? So yeah, I'm glad you said that because when I do these, like in the previous example for S3, they were unique subgroups, but for some of them, there'll be conjugate subgroups that they're isomorphic but not equal. There's another isomorphism, you know what it is? This one's kind of interesting. With an asterisk by it, because they don't all work. This is one of the strange things about S4. Here's what I mean by that. One Z2 might look like this. There's one copy of Z2. But it didn't work, right? Because no matter how hard you stare at that thing, there's no way to take 1 to 3. Right? This one is intransitive. It doesn't work. How can I make it? There's one subgroup. It's a weird. This copy, I mean, when I look at that, it's not even clear that it's a subgroup, right? I mean, you should probably multiply a couple of these elements. This one times this one is this one, and so forth and so on. So there's this weirdo Z2 in here. Notice also that, let me also point out, there's another problem with this. Well, no, I think right. Notice that this one is contained, this one's contained in the A4 subgroup. Right, because all of these are even permutations, but this one is not. But anyway, this is actually, and it's fairly easy now to see it's transitive, right? If you believe this is a group, 1, 2, 1 goes to 3, 1 goes to 4, 2 goes to 3, 2 goes to 4, 3 goes to 4. So there are 5 isomorphism classes of transitive subgroups of S4. Right, already. Okay, maybe you've got some experience now. You might be able to rip off 4 for me. There's actually 5 again. Anybody know what 4 of them are? How about 1 of them? Yeah, there you go. That's the spirit. That's 5. A5. What else do you think? In the same sort of way that I did cyclic, a cycle of length n should do, right? So this can be C5. And Preston's observation, I get C5 and jump to D5, right? The other one's here. The Frobenius group 20 elements. It is generated. This subgroup of S5 generated by this. Again, there's isomorphic copies of this all over the place in there. You might mess around with this, and this is like a semi-direct product. And you've got a 5 cycle and a 4 cycle. You might look at the conjugate of this and see what happens. In fact, yeah, you might, but this actually generates a group of 120. And I know it has to be, once I know that this doesn't do something stupid like generate all of A5 well, it can't generate all of A5 because it's got odd cycle in it. Well, even cycle is not a permutation. Be careful with words here. Once you know this doesn't generate all S5, it has to be transitive, doesn't it? Right? Because it contains a 5 cycle. That one, I think if I remember right, I'll look this up. I've got a neat table on my regular papers. I think that there are 60 transitive subgroups of S6 of the isometric. It's too many to list. But I can tell you some of the play. Like you're going to have S6, you're going to have A6, you're going to have cyclic of order 6, and in fact, you're going to anything that has a 6 cycle in it should be transitive. So there'll be all kinds of exotic groups in there. But this is kind of the cool thing. And yeah, I can fire some of this on the way out. How many of you have ever arrived, seen, played with the cubic equation? Right, where did you find it? Like in an old book or on the internet or say some moldy old book or something? You quickly see why. Okay, I see why, the people that I, went to McDonald's with in high school probably should be exposed to this kind of thing, whatever. I get that. But everybody's exposed to the quadratic form, right? Notice that there is a universal sort of formula for the quadratic equation. And that's essentially because what are the possibilities for the Galois group of a degree 2 polynomial, say over the rational numbers? There's actually 2 possibilities. There are 2 possibilities for the Galois group of quadratic, right? One of them is 1, the identity. What happens when the Galois group is 1? What does that really mean? It means that your polynomial already had rationals, right? So the Galois group is 1. That means that there's nothing other than identity. So your quadratic actually wasn't irreducible. It broke down into 2 linear factors. And the only other possibility is it's got Galois group Z2. So it flips back and forth between the group and its conjugate, right? This is why the quadratic formula, at least from our perspective, is easy, right? Because you've got the plus or minus. This is why the cubic formula was more complicated. You might have Galois group. Well, you might have Galois group 1, right? The cubic, actually, it sort of subsumes the quadratic as well. You might have Galois group 1. You might have Galois group Z2, but that's really stupid because that means the polynomial wasn't irreducible. It factors into a linear and an irreducible quadratic. So we'll assume that the polynomial is in fact irreducible of degree 3 to make it easier on the way up. There are 2 possibilities for the Galois, right? It could be all of S3, right? I'll give you an example. X cubed minus 2. You remember when we played with that example? Right, it had Galois group S3. These are actually harder to find, even though we got some Galois. This is worse, and we will get to cortex. And this one is impossible. And we'll get to that later because there are 5 possible Galois groups. If you draw this, this, and this Galois groups, then you can solve the polynomial in terms of radicals. If you draw these 2, you can't do it. It can't be done. That doesn't mean polynomials don't have solutions. It's just you can't write them in terms of radicals, right? And this is because these 2 groups are solvable, just parsing. And these These ones are solvable. Okay, we'll talk more about that next time. Any questions? Well, I hope to see you all